齐威佑亮宇启恩 and 丽君 Glad to see you guys surviving the midterms. Oh, hi Bosch. Hi Yin-Yo, good afternoon to you as well. Hi Jessica. And Bing Ray. Hi Chimao. And you guys are early. You know what? Yeah, it's a blizzard background. It's in fact a train riding in Siberia, I guess. Yeah, also I find this type of background sound soothing, that calms me down. Yeah, it does feel like you're flying, right? Flying on a broom, for example. Hi, Jiayou, Qian, and Jieming. You're ready to sleep? So there's, certain magic when a train riding on a train rack. Yeah, there's this nice rhythm going there. That puts me into sleep also very well. Imagine that the real world is blizzarding out there, and within Taida we are warm and ready to learn more. Good night. Yeah, Lawrence, it feels like it's about time to say good night. Hi, Shanti. Kristen. And I don't know about you, I do feel like it's turning winter here already. Don't you think so? And that's open. Okay, so today's lecture is going to be fairly easy. In fact, tomorrow's lecture is also going to be fairly easy. All we will be doing is to transition from selective repeat, the second pipelined RDT, to TCP's RDT. Okay, so today, 2 parts. We first talk about selective repeat and then TCP. And the to-dos, the announcements, of course, these are the usual assignments due, PA6 and quiz 22 to 24. I would like to look a little bit ahead of time as well, because PA7 will be doing next Saturday. Okay, not the coming Saturday, but the next Saturday. And the reason that I need to mention it is because PA7 might be as challenging as PA3. Okay, so I know PA5 and PA6 that's doing this Saturday, they are fairly straightforward. So PA3 was not, PA7, the one due in 2 weeks from now, is a little bit challenging, okay, much like PA3. And, sorry guys, you guys are probably just walked out of the midterm. You know what, for this course, exam number 2 will be coming also in about 2 weeks. Okay, but the styles will be completely the same. It will be longer than usual, longer than you can complete, but they are serving a purpose. Okay, all I look at are just how you do relatively to each other. All right, and we may now begin with the first topic. And before we do, hi Yuxiang. Good. So the attendance has been very good. I was actually quite surprised. And that's overview selective repeat. Selective repeat. This is the second big categories of the pipeline RDT. So its design is pretty much the opposite of go backend. So in go backend you have cumulative ACK. So the sequence number in the ACK there is to indicate all the packets before these particular numbers are received correctly. But in selective repeat, the acknowledgements are individual. So one acknowledgement packet per data packet. The sequence number in the acknowledgement is only to acknowledge one data packet. In go backend, we have one timer for an entire flight of packets. When that timer times out, we retransmit the whole flight of packets. In selective repeat, the opposite. We have one timer per data packet. When that timer times out, we retransmit just that data packet. Right? So, receiver will acknowledge each correctly received data packet individually. Sender will only retransmit a packet when the timer for that packet expires. Very straightforward. The slight tricky part of the selective repeat is at the receiver. Okay, we now have to buffer packets arriving out of order. The reason for this is very straightforward, very simple. If we send packet 1, 2, 3, and 1 arrived at the receiver, 2 get lost, 3 arrived at the receiver, you cannot be just extracting the data bits out of packet 1, pass it up to the upper layer, and not passing the bits of packet 2, and immediately pass the data bits in packet 3, and then later pass the data bits in packet 2, because that way you get bit sequences that is out of order at the application layer. And our definition of RDT is that all the bits arrive reliably and in order. So receiver here in selective repeat, the implementation gets complicated. You need memory space to store temporarily the packets arriving out of order. You wait until all the gaps are filled, and then you pass all the data bits up to the application layer in sequence. The only thing that remains the same is there is still this sending window, which is limited by n, from the base to base plus n. Now, be a bit careful in selective repeat though. What we are limiting there is the sequence number of the unact packet. So what is the maximum sequence number there can be unact. As opposed to in go back n, we say n being the number of unact packets. The reason that I'm saying you need to be careful is because of this. From the base to n plus base. Yeah, there are yellow packets, alright, and after the yellow packets, the blue packets. In go back n, they're just gonna be yellow and blue. So the number of yellow packets maximum will be n. In selective repeat, because we have individual acts, so some of the yellow packets can be green, like this. So even though they're turned green, but that doesn't mean that they will include these 4, okay, into the window, like this. Okay, no. So what we're restricting is the maximum sequence number that can be unact, not the maximum number of packets can be unact. Okay, just to make sure that's clear. And the receiver of selective repeat is, as we talked about, more complicated. It also maintains a certain data structure, tracking the status of these packets. So we also have a window size here at the receiver. The base is now called the receive base. So receive base is always pointing at the first packet expected but not yet received. And there could be a number of these pink packets around. So these are the packets arriving okay, but out of order because there's a gap before it. So those are the out of order buffered packets. The blue ones are reasonable, okay, packets that are expected next. Okay. The black ones are just not possible. So if we receive packets after receive base plus n, we'll be just treating these as maybe hackers injected packets, spoofed packets, things like that. So that was the overview. Now the finite state machine of selective repeat. And now the selective repeat finite state machines. This is the sender side of the machine, and this is the receiver side of the machine. And you might be going, wait, they don't look like FSM at all, right? Because previously we have like states, right? And the number of transitions like these. Yeah. What I'm doing here is to do textual representation. So what I'm saying is essentially, yeah, there are still 3 transitions. So first transition is triggered by this event, the data from above. Okay. Second, the timeout event. Third, triggered by receiving an acknowledgement packet within a particular range. Yeah. So later on, you will see what's nice about writing the finite state machine this way. because it looks almost like a pseudocode, isn't it? Right. So the sender side is looking like a switch procedure, where when there's the data from above event switching in, then we do this. When there's the ACK packet being received switching in, then we do that. So now let's go over the finite state machines of the senders and receivers. Sender side, when there's a call from above, okay, if the next available sequence number is within the window, yeah, send packet. And you know how to do the next available sequence number, whether it's in window check, right? So the next seq num should be less than base plus n. Second is the timeout event. If our timer times out, and that is for packet sequence number n, we retransmit packet n and restart timer. Straightforward. If we receive an acknowledgement packet, we extract the sequence number and check if it's within the send base and send base plus n subtracting 1. So that is saying, hey, whether the ACK is within the reasonable range, right? Because the send window is only this big. If we receive ACK before that or after that, that's just weird. Okay, let's just ignore those. So we'll only be handling ACKs that's within the send window. Now, once that's the case, we mark packet n being received, so turn it to green. If n smallest unACK packet, so if n here is also the smallest unACK packet, so we turn that into green. There could be a number of other greens following that. Then we could what? Advance the send base all the way to the next yellow packet. Okay, so advance the window base to the next yellow packet, which is the next unACK packet. All right. So this is sender's actions, depending on what's triggering the sender's finite machine to take transitions. Similarly here at the receiver end, there are 1, 2, 3 transitions. First transition is if we receive a data packet that's within this range, the receive base and receive base plus n minus 1. So that is reasonable, okay, as expected. Then we send individual acknowledgement. So if it's packet n, then ACK n. If this packet is not expected, so meaning it's out of order, then we will buffer them. So these will be the pink packet, all right? Now, if this packet is actually coming in and filling one of the gray packet, so unreceived previously, but expected, then we can pass all the packets suddenly in sequence, all in pink, up to the application layer. So that's deliver those, okay, in ordered, and advance the window to the next, not yet received, but expected packet. So to the next gray packet. All right, so this is when we receive a data packet that is within the receiving window. If we get a packet, okay, that comes in, but it's actually in this range, receive base minus n to receive base minus 1. What is this? Okay. We are actually sending an ACK for that packet back. If you recall, it could happen, right? The ACK packet going back to the data center, if that packet is corrupted, the sender there is going to wait until the timer for that packet times out, then retransmit the data again. But that data has already been arrived at the receiver previously. And that's why the receiver sends an ACK back to the data at the first place. And that's before the data is found corrupted at the sender as well. Right? So in that case, we still need to send the ACK for that packet. Okay, do not ignore this. Otherwise, that timer is going to fire it again and again, and the sender there is going to retransmit the same packet again and again and again. Right? Third transition, otherwise, or the default, I'll just ignore. Okay, so receiver, pretty much do nothing in case it's packet
not within the receiving window or not one receiving window before. All right. So those that are outside, just ignore it, because chances high that they're coming from hackers or previous connections, and the data somehow, the packet somehow gets stuck in the network for too long, and it's gonna be useless anyway.
All right, so that was the finite state machine. There was a question from Yu Hao. What does it mean, a packet arriving out of order? Because packet carries a sequence number, right? Packet 1 comes in. If it's in sequence, you expect packet 2 arrives next. But if packet 3 supposedly in sequence should arrive, but we skip that, the receiver suddenly receives packet 4, then packet 4 there is a out of order packet. So in sequence, meaning 1, 2, 3, 4, 5, 6 in order. Out of order means 1, 2, a gap, 4, another gap, 6. So 5 and 6 in the second scenario will be out of order packets. So Yuxiang, you can think of out of order packets are the packets arriving, but there are some gray gaps before them. So these packets will be received and buffered temporally because they cannot be passed up to the application yet. Because the applications might be thinking these are the characters before some of the characters that are still in gray in the receiver's buffer space. So to maintain all the data coming to the application in order, we buffer these out of order data and wait until all the data in order arrive, then we pass everything up to the application layer in order. Okay, good. Now let's take a look at an example of a selective repeat.
And let's also walk through an example of selective repeat, just like we did one for go backend. So that example in go backend is actually harder to analyze. This one, on the other hand, relatively easy. Now it looks very much like the example in go backend. So window size 4, and we start from base 0 and the next seek number 0. Getting a call from above? Yeah, because the next seek is less than base plus 4. Therefore, we generate packet 0 and send it out. And we go on until we hit next C equals 4. And that is not smaller than 0 plus 4 anymore, so we wait. All right. Now, over at the receiver side, scenario similar, receiving packet 0, but the receiver's action different. Okay, for packet 0, we send individual ACK 0. Receiving packet 1, we send individual ACK 1. Well, not getting packet 2, but we'll be getting packet 3. And out of order, so we buffer and send individual packet, individual ACK packet, ACK 3. So ACK 1, ACK 0, ACK 1, and ACK 3 will go back to the sender. Now, sender, upon generating packet 0, packet 1, packet 2, and packet 3 will all start the timer individually. So T0, T1, T2, and T3 will all be ticking, no worries. Okay. Now, ACK 0 now comes back to the sender. Sender receiving ACK 0 will do what? Clear packet 0. So that packet will turn green. Is it in sequence? Yes. So we advance window. Yeah. Advance window by 1 to the next unacked packet. Upon receiving packet 1, also, advance sequence by 1 because it's in sequence. And hey, so base is changed to 1 and then to 2. So that allow us to send packets more, right? So 4 is generated, 5 is generated, and they're being sent out. Well, packet 2 did not get acknowledgement, but we get what? ACK for 3. All right. So what do we do there? Yes, we actually release packet 3 So we turn that into green. But hey, packet 2 there is still yellow. All right, so this green packet, packet 3, is not the smallest NI packet. So we cannot advance the window size further. We cannot advance the send window further or the base further. All right, so cannot be sending more. So still wait here. Okay, so this part of go back and selective repeat similar, right? But now, look, packet 4 and 5 will go to the receiver. Receiver here receiving 4, out of order again, buffer, send ACK4. Packet 5, buffer again, send ACK5. And those will go back. Here, timer for 4, timer for 5 will be fired because there's one timer for individual packets. Okay. So finally at this time point, yeah, timer for 2 finally expires, and therefore we resend packet 2. Packet 2 goes out, received. Finally, this is the smallest unact packet, and all the packets subsequenting packet 2, 3, 4, 5 can be passed up, okay, in sequence to the application layer, and we send back ACK for 2. All right. So simpler.
But what would happen when the sender receives Act 2? Okay, think about it as we start quiz number 22. Okay, so quiz number 22 is actually asking you to compare go back N and selective repeat, these two pipelined RDT mechanisms, in these 4 ways. Q1 asks, which of these two tend to use more network bandwidth, okay, to retransmit for losses? Go back in and selective repeat. Which one use more bandwidth to retransmit? Q2, which one requires more memory space at the receiver end? Q3, which one requires more memory or more timer at the sender end? And Q4, if you are a programmer, okay, that needs to implement a pipelined RDT, which one would you pick? If you want to do this in minimum effort, okay, which one would you pick? And tell why. Okay, interesting. I guess Q1 was quite obvious, isn't it? Because go back N does have this behavior of retransmitting for a whole flight of packets. While selective repeat, if you retransmit, you only retransmit for the packet that is indeed lost. So Q1, I don't see debate there. Q2, which one requires more memory space at the receiver end? We just saw an example, isn't it? When packet arrives out of order, meaning there's a gap, okay, before the sequence of the packet arriving, then we need to buffer it. We cannot pass it up to the application yet, because the application is actually waiting for the one that's not yet arrived. So in selective repeat, we see packets arriving out of order being buffered. Yeah, so for Q2, also quite straightforward, right? Selective repeat. Q3, for Q2, also quite straightforward. It's a selective repeat. For Q3, more timers. Okay, so this one is also very obvious. In go back N, we have only one timer for the entire flight of packets. But in selective repeat, the timer is also for individual packet, just like the ACK is for the individual packet. So selective repeat, I guess for many of you, is more intuitive, right? One timer for one packet, one ACK for one packet. But then you see, Selective repeat, you need more memory space there at the receiver. You also need to start an array of timers at the sender. If you are a programmer implementing selective repeat, wow, okay, you need to allocate more memory space here, there, creating more timers here, there. So I see also that for many of the teams so far, you guys prefer go back in because you just need to create one timer, right, at the sender. And there's no need of handling these buffer for packets out of order. Yes, at least the receiver side is super easy, isn't it? Sender side is also easy because it's just one timer. You just use one variable, timer. Okay, so you either cancel it or you start it or you refresh it. It's not an array of timers like in selective repeat. You need to look at the X sequence number and find out which timer you should cancel or restart. Yeah, go back in is indeed easier to implement. It's less effort to implement. Okay, so you see, selective repeat versus go back in. Go back in, although a little bit complex, right? Because every time you need to retransmit, you retransmit for the whole flight. But it's easy to implement. Selective repeat, it's very intuitive, straightforward, easy to debug most of the time. But you do require memory space here and creating timers there. Very good. So that was to contrast the two mechanisms. There's just a little bit something that we need to talk about selective repeat or go back in general. That's related to the window size n. Okay, that actually determines the sequence number space we could use. Okay, if you have n, the sequence number space somehow needs to be larger than 2n. So let's take a look at this video here explaining, showing it in scenario. If that rule is not conformed, we might run into problems.
The last bit of selective repeat is this. Let me show you this case. There are two scenarios, okay? But from the reviewer's point of view, they will actually look the same. Right? And this is due to the fact that the sequence number here, the sequence number space, and the window size there is not set in a way that we could tell individual packets apart. Those who are sent earlier versus those who are sent recently. Okay, so the example goes, sequence number, only 2 bits, so there are only 4 different numbers. Window size, 3. Right. So the selective repeat sender side will look like this. Well, the window size is 3, so we can only send 3 packets back to back of each other. So packet 0, packet 1, packet 2 goes out. Receiver here receiving 0, 1, and 2. They will then send back Act 0, Act 1, and Act 2. So Act 0 here arrives back at the sender first. And this is in sequence, so we advance the send base. And we generate yet another packet to go. All right. And the next act, that's going to advance the send base further to 2. All right. And we generate yet another packet to send. And the next one will be what? Yeah, carrying sequence number 0. Now, if packet number 3 did not arrive at the receiver, all right, receiver here will see, all right, I got the packet 0. And you know what? Within my window, I am indeed expecting someone carrying sequence number 0. So this one will be what? Buffered. And an act of 0 being sent back to the sender, isn't it? Right. So that seems to be fine. Yeah, this is the no problem case. Wait until you see the next one. Here's the next one. Same scenario, window size only 3, and we have sequence numbers. There are only 4 of them. So we send packet 0, 1, and 2 out. Receiver here generates ACK0, ACK1, and ACK2 back. But unfortunately, all of them are lost. So timeout is going to happen and retransmit packet 0. This packet 0 will go, and receiver here will say, hey, you know what? I'm expecting packet 0. It's within the receive window. So buffer and send back ACK for 0. Sounds familiar, isn't it? Because that's exactly what's being done here in the first scenario. So from the receiver's point of view, identical. Also, buffer the packet and send back ACK0. But the thing is this, at the sender side, you see, this packet 0 is a retransmission of the first packet 0. But this packet 0 here is actually the second packet 0, no longer the original, the first packet 0. All right. So if packet 3 here arrived at the sender, the sender is going to what? Clear that gap and pass 0 up to the application layer. Before that, pass, of course, packet 3's bits into the application layer. So 3 and 0's data bits will go to the application layer. But look here. This is packet 0. When packet 3 finally comes here, it's going to clear and send packet 3's bits as well as this retransmission 0's bits up to the application layer. So you get unwanted duplicates. So you do have a situation here. From a receiver's point of view, it actually sees no differences in the two scenarios. You get duplicate data in the end in case B. So we need to be careful here to prevent. Packet 0 here and packet 0 here obviously are two different packets, but being confused as the same packet. So according to case A, we'll actually pass packet 0, these bits again to the application layer. Not good. Right? So in order to tell this packet 0 and this packet 0 apart, we have to think, what is the worst case? Can we use a sequence number such that we will not be confusing this packet from this packet? So a new packet should be farther away, should be carrying a sequence number that's farther away from an earlier packet. And no worries, if you look at this, case number 2, case B here, is already the worst case that I'm illustrating. So in this case, we're seeing that the receiver is advancing the receiving window one after another. So receiver is saying, hey, everything is okay, let's move on. But sending side here, not getting any ACKs back, hesitates and waits and waits and waits and not moving. So you have one end moving really fast and the other end staying. So you see in the end, the worst case is what? The sending window never really moved, but the receiving window moved the entire end. Right? So they are actually end apart. If you want to make sure that none of the packets still in the sending window will be confused with the packets in the receiving window, what do you need to do? Isn't it obvious? The sequence number, make sure that the space is larger than 2 window sides, right? Then, hey, packet sequence 1 will never appear again in the next window, in the receiver's window, all right? So you will never have the trouble of confusing an old packet from a new packet. And that is why the sequence number space here needs to be larger or equal to 2 times the window size.
Right, I hope that's clear. And there was a question from Botit. Yeah, you see, computer system is a man-made world. What we do a lot is to use sequence numbers, and because of the number of bits we have in the packet header is limited, so that sequence number range is also limited. So if the range is too small, then you see I send packet 0, 1, 2, 3, and out of range, then I need to rotate back and use a number that I have used before to send a new packet. Okay, so if the sequence number range is only 0, 1, 2, 3, then after 3 I use 0 again. 0, 1, 2, 3, 0, 1, 2, 3. Okay, so that's why you see packet 0 that we have already sent before. How come, right? We are sending it again. But these 2 packet zeros are actually 2 different packets. Okay, so sequence number range, it's limited, but it cannot be smaller than 2 times n, the congestion window size or the sending window size. Okay, so now we move on to the TCP part. First is about 7.5 minutes an overview.
And this is 3.5, connection-oriented transport, particularly the TCP protocol. So in this particular section, we're definitely going to talk about the RDT implemented in TCP. Now, provided the background, okay, very extensively in 3.4, you should be able to understand TCP's implementation of RDT, TCP's design of RDT. Now, in addition to the RDT in TCP, we are also going to talk about the packet format of TCP. And that is what the segment structure meant here by the textbook authors. And then there are 2 minor functions, but necessary functions in TCP. One is called the flow control. The other is called the connection management. And this is the overview. TCP we know already, just like UDP, it's what? End-to-end process-process communication. So end-to-end there can also be referred to as point-to-point communication. We have a sender process and a receiver process. Now, in this connection here, what we're doing is to do reliable and in-order data transmission. Now, what's a little bit unusual when we talk about TCP is this. Instead of earlier, when we were talking about the general principles of RDT, we are counting the data by what? Packets. Packet 0, packet 1, packet 2, packet 3, so on and so forth. But in TCP, we count data all right, but we count the data by the bytes. By 0, by 1, by 2, and so on and so forth. So that connection here, when we are passing data around, we are actually passing a stream of these bytes. Right? So there's no more message boundaries, or there's no more packet to packet separation. Right? And last, this is actually telling you ahead of time that TCP's reliable data transfer is doing this, the pipeline-based RDT, so that we have a window size there where the size n is definitely larger than 2. And so we could have multiple packets in transit so that the utilization of the connection there can be higher. Now, what we don't know quite yet is this window size is also used not just for reliable data transfer. Later on in section 3.6 and 3.7, you will also hear it's also for the congestion and flow control. Okay, so there's going to be a window size for flow control, and the window size for RDT is also used, okay, for congestion control. And conveniently in flow control, what's being done is the receiver will every now and then tell the sender, hey, you might want to slow down or you might want to speed up depending on how much the buffer space is occupied at the receiver side. You see what happened at the receiver end of the TCP is this. Data will come in continuously from the sender. Data will be extracted and passed up to the application layer process. So there's an incoming rate and there's also an outgoing rate. When the outgoing rate is slow, incoming rate is fast, then you see the buffer space is quickly exhausted. Okay, so at that point, receiver tells the sender, hey guys, slow down. All right. Now, the other way around, if the buffer space is very empty, then telling the sender, feel free to send more. So flow control there. Okay, mainly allowing the receiver to tell the sender, hey, slow down or speed up, such that there's no congestion occurring at the receiver side. Because if the incoming rate is high, outgoing rate is slow, over time, when the buffer is exhausted, the incoming packet, incoming data will be what? Will be dropped. Okay, so delay long, and you see also data loss there, right there at the receiver. So this is to avoid also congestion, but it's a bit weird. It's actually to avoid congestion at the receiver side, not quite in the middle of the internet. Okay, so when I say in the middle of the internet, I actually meant congestion in the core of the internet. Sender process, receiver processes are what? At the end of the internet, at the edge of the internet. So flow control there is to try to control the end processes such that there's no packet drop at either end. Congestion control, on the other hand, is to control such that there's no packet drop or congestion in the middle, in the core of the internet. And TCP, being connection-oriented transport layer service, is sending some messages at the beginning before data can be transmitted. So there are some handshaking being done right before the data exchange. And these handshaking messages are there to set up the initial states of the sender and receiver. And that is called the connection management part of TCP. Last but not the least, there's a mindset change here in a TCP connection. Data traveling in a TCP connection is now full duplex. What I meant by that is the data flow is going, bidirectional. Okay, so two processes or point-to-point, will be sending data this way as well as this way. Now, why is this a major mindset change? If you recall in 3.4, when we were talking about these reliable data transfer mechanisms, we always say what? This is the sender side of RDT, and this is the receiver side of RDT. What we are saying there implicitly is also, this is data sender side of RDT. This is the data receiver side of the RDT. Data receiver there, receive data. It transmits something as well, but it's transmitting only what? The feedback messages, the ACMEX messages. The receiver there does not send data. So TCP here you see being more general. Data can go either way. So the two processes will be implementing both the sender and receiver finite state machines. And the last bit is this. MSS, a special term that is referring to this, the maximum segment size. If you recall, a packet at the transport layer is called a segment. So maximum segment size is essentially the maximum packet size. Okay. In reality, in actual TCP implementation, we're still sending data packet by packet. But the sequence number we'll be checking to do reliable data transfer is now counting the bytes of the data, not the packet numbers of the data.
And the last video, about 7 minutes, here is to introduce the packet format of TCP. It's very important. It will set the base for the lecture tomorrow.
TCP Signal Structure, aka the packet format. It does look a bit complicated, definitely more complicated than the UDP packet. If you recall, in UDP, we do have these fields: source port number, destination port number, as well as the checksum. Okay, so all these are what called the header fields. So in TCP packet, the header part is substantially larger. While the data part, it's still variable lengths that could be large, could be small. Oops, yeah. So the overall structure in TCP packet is actually very similar to UDP, two parts, header and data. The main difference is where? The header part. Okay. So some of the header fields repeat itself. We see source port number and destination port number, as well as checksum, also in TCP packet header. But what else in the UDP packet header that we don't have, or we do have in TCP's packet header? And here's UDP's packet format. So we do see source port number, destination port number, checksum. And what else is in UDP's packet header? The length. So that is the entire packet size, including the header as well as the bytes in the segment. So data and header together, okay, in this field, the lengths. And do we have lengths here in TCP's packet header? Well, if we look around, yeah, something slightly similar. It is lengths. Okay, so LEN is actually short for length. But it's only the length of the packet header. So this part versus UDP's length, quite different. Semantic, very different. So UDP's length actually talk about the entire packet size, but length here is only covering the first part of the entire packet structure, the header length. Do we have lengths in TCP's packet header? We actually don't. The thing that we have the closest is this, the header length. So the length in TCP packet header counts only the size of the TCP packet header, while the length in UDP's packet header counts the entire UDP packet. Given that we're already talking about the header lengths, why don't we talk about these special bits, okay, special flags in the TCP packet header? First is the A flag. Okay, so this is called the ACK flag as well. When it's turned on, when the ACK flag is on, that's indicating that the acknowledgement number here is actually valid, meaning that the sender of this packet is trying to tell the receiver that it's trying to acknowledge certain bytes being received. Okay. And these three R, S, and F bits, they are there to indicate packets being used to do connection management. So for example, SYN here, the SYN packet is to set up connections. The FIN packet, which is Latin for the end, conveniently, okay, is to tear down a connection. RST, or the R bit here, means reset, that is to re-establish the connection, to re-initialize certain parameters between the sender and receiver of a TCP. And P bit, P stands for push, that is to push data now. So this is to actually pass the data out as soon as possible, but it's generally not used. Just like the U bit, this is urgent, so this is indicating that whatever data is here is urgent. So pass it out through the network or to the application layer as soon as possible. Okay, so you see urgent, the purpose, and push, somewhat similar. The ambition of the network engineers much early on is also that hopefully a data network or the internet can also allow urgent data being sent, just like we could make it 911 call, or in Taiwan 110 call to get police's attention or the fire department's attention as quick as possible. But unfortunately, the way the internet is designed is just not very good for urgent, critical data transmission. And yeah, we said that these are not used, so there are a number of bits not being used. But the fact is, actually, there are two more bits being used. It's called the C bit and the E bit. Now, these two bits are not really for reliable data transfer service, not for connection management purpose. They are actually there for congestion control. But it's not quite the congestion control implemented in TCP though. Okay, it's just that the engineers are expecting, okay, later on TCP's congestion control can be extended, okay, together with the core of the internet such that we could do better control. So there will be two more bits we'll have to talk about, but it will be at the end of chapter 3. And that takes us to, the urgent data pointer. So this is actually working with the urgent bit. When the urgent bit is on, then the transport layer of TCP is going to look into this pointer and then grab whatever the data that's here indicated by the pointer. So this data here will be extracted and passed out as quick as possible. And receive window here. Yeah, this is the window size for the flow control. If you recall earlier in the overview, we say flow control is for the receiver to tell the sender, hey, slow down or speed up. And when the slowdown is to be communicated, receive window here will be a small number. If the receiver wants the sender to speed up, the receive window there will be larger. And the last two fields in the header are these. The sequence number as well as the acknowledgement sequence numbers. So these are exactly for the reliable data transfer purpose. But keep in mind, we're now counting the bytes, okay, not packets.
And that's all for today. I'll see you tomorrow, 10:20, and we'll start talking about the finite state machine of the reliable data transfer mechanism in TCP. All right, so good timing here. Go off to the next lecture if there's any. If there are any questions, feel free to type up on the chat. I'll stay up for just a little bit longer. Okay, bye. Bye. Maybe the sequence number length is limited. You know what? It is. It's actually the longest field in the whole packet header, but it's still limited. To be exact, it's 32 bits long. Okay, bye. Bye, Yunqi, and bye, Ida. So is Yanjun. I think we occasionally have artist students. I think Bohid is probably, Badhid is probably from somewhere else. Mm-hmm. Yeah, bye, Bing Rui. Yeah. Okay, bye. Bye, Livia. Okay, I think it's a good time to end the stream now. I see you tomorrow. Okay, bye, Yuxiang.